I'll just leave the floor to you, Daniele.
Yeah. Yes.
Yeah, I hope you enjoy the session and this part.
Thank you very much.
And thank you, Daniele. And so I'll see you
See
around.
you later.
See you later.
Goodbye. So what I what I originally planned to do today, which I think we can continue like that. Can you hear me all right, by the way?
Yes.
So in this lecture, basically, I want to give you a little bit of what I consider being the cutting edge questions that we're now dealing with in the area of numerical methods for I would say neurobiological networks. The premises are that we're going to still use the neural fields as a prototype, but pretty much everything I say is portable. And I would like to discuss with you 3 of the hot topics. Let's say that they were the first one we have already started discussing last time. That is really, I would say, rigorous derivation of finite elements and collocation schemes for spectral schemes for neural fields. And this is something that I will just go quickly over because it's effectively a recap of what we have done last time and perhaps give you some more results rather than analysis of what we do. And then I will start discussing networks in which there is randomness attached. So these are now situations whereby some of our parameters are no longer deterministic, but they're random. And towards the end of the talk, I'll do a demonstration on my iPad, like if it was a board, to give you a flavor for what we mean by random parameters. And then I will show you results at the end of neural fields that are forced stochastically. These are also very exciting for me. So this is almost a research talk in the sense that I will really present stuff that we are currently researching on with this group of supremely talented individuals. So Francesca has started a PhD at the VU a couple of years ago, at the same time as Khadija works in Radboud University. And what we are trying to do there is to have a small group of research that is dislocated between the VU and Radboud, where Gabriel Lord is. Svetlana Dubinkina is another colleague of mine who works on data assimilation. And what we're trying really to do here is to bring all the method and technology that are typically available for geoscience applications to the brain. And that is really the motivation that got me into developing finite elements first, because the idea is that all of these methodologies start from solid discretization of deterministic problems on which then you build up. If you fancy joining us, we also are happy to have just general discussions about numerical methods for neurosciences. And this is our Zulip channel. You're very welcome to just join it at any time or drop me an email for it. So the main idea, you've seen already this picture, is that we want to start treating the brain as an organ. And for doing that, we need certainly to couple activity to other physical processes. So we're looking at really doing some form of multiphysics methods for the brain. And as I announced, as I told you in the past days, while PDEs have a well-tested suite of schemes for neural fields and similar methods that are still in the making, similar models that are still in the making, we're not yet there. So we're building up this type of framework. So in this talk, but this was already true last time, the brain will be like a three-dimensional cortex. You have already, it can also have a thickness. The example we discussed, the tutorial that I gave you actually was relying on D being a surface in R3. But if instead of using triangular element, you use tetrahedral elements, you can also cover surfaces, manifold with that three. three manifolds in R3. But the equation of motions look identical effectively to the one that you have seen. And now G for this talk will be the forcing, and V will be the initial condition. And this is really the equations that you now have seen multiple times. Also, because of what you have seen in, I think, lecture 1, everything that I will write really on the board today is also immediately applicable to connectomic models. So connectomic models, the best way to look at them is that they're discrete versions of neural fields. So for those models, there is no need to discretize space. You can view it as somebody has already discretized space for you. They give you masses. But the methods that have to do with random and stochasticity that I want to talk today, they're immediately applicable to connectomic models, or if you have a neural field with more than one population, they're also applicable. And if you want to couple many of them, you can, if you want to do a hybrid in which some parts of the model are connectome and some parts of the models are not connectomes, then the methods are immediately working. So that even the theorems that I will cite are already applicable. You may wonder, why do I want to couple these type of things? You want to couple these type of things, pardon, I'm just trying to go back. You want to couple these type of things, these type of models, because perhaps, let's wait that the brain spins once again. Let me stop it here. Perhaps in addition to the surface of the cortex, you also have areas that you want to model, like the medulla, like the amygdala, like limbic areas, like the thalamus, that are down here, that are not necessarily cortices in 3D. And so it's very easy to come, well, not very easy, it's natural to come up with models in which some parts there is a continuum cortex and some part instead there is a mass or few masses there. And adding masses comes for free in the formalism that I will discuss today. And then I have a claim. I call it a claim because I have, some of the maths that I am using is a little bit specific to the neural fields as you've seen them. So I don't have a proof, but there is really no reason that this shouldn't work. I just need an excuse, or perhaps somebody who is willing to do that with me, to just translate everything to this more general framework. I can move this framework, I think, and I have numerical evidence for this, to cases where you have multiple populations, but that's easy. And then you have a local nonlinearity. So you see here, there is this function, this object called N1 to NP. That's a nonlinear. For the neural field, that now is just minus U1, minus U2, etc. But in general, the more general models have nonlinearities there that are local. And it's straightforward to apply these methods in that context too. It's just I have not done it yet. And these new models are these new classes of neural fields that I've not talked to you about, that are called second generation neural field models or new generation neural field models, whereby, and the reason why they're more exciting is that because they really come as exact bottom-up mean field reductions of quadratic integrated infinite models. So the idea is that you put together many models of single neurons that are not Hodgkin-Huxley. They are, they are quadratic integrated infinite models. So these are one of these models that they spike, so to speak. And we now have a theory that takes us to the mean field limit for those. So you will see, for instance, that there is no firing rate function. So if you look at where the kernels are next to the W, there is not f of u. There is not a nonlinearity there. So you don't have to make up a firing rate. The firing rate is one of the variables that you are evolving at the same time as u. And they act nonlinearly with u in that n function. So this is a very exciting thing to do. If you're keen, let me know. So this is a very good slide to internalize for today's talk. It basically tries to express a neural field, separating the input to it on the left and the output on the right. It says, if I have to run the neural field at that scale, what will I do? I have to choose a synaptic kernel, choose a rate function, choose an input, choose an initial state, simulate, and out comes a voltage. Let's say an activity variable, but it can be a voltage. And these are super popular models. In fact, I've been preceded in my studies by many illustrious collaborators, some of which are mentioned here. Let's have a look. I mean, you have seen this before, but let's have a look at how, for instance, W is. At some point, I got a question in the past 2 lectures, and the question was, how can I choose W to be distance dependent or not? And this really depends on the scale. So often my community chooses distance dependence kernels or variations thereof, like the one you're seeing here, when you're representing small bits of the cortex. So when you're in V1, that may be an acceptable approximation. You're really looking at a kernel in a small bits of the cortex. And even then, you can make the cortex heterogeneous, but you can start from a homogeneous kernel. So this is an hypothesis that is a modeling hypothesis that is more easily justified in situations where you're trying to model small bits of the cortex. Now, what I'm going to show you is what happens with the data that we get at large scales. So if you don't look at the cortex over there, but rather you look at the cortex on a large domain and measure what's the average number of wirings between 0.1 and 0.2 on the cortex, they come up rather than me, with diagrams of this type. So of course in here, there is this is literally, by the way, one of the W's that I gave you last time, except I made up the W, just taking distance-dependent kernels, and now we would be reading the W from tractography data. Tractography is this, it's a scanning technique that allows you to effectively reconstruct bundles across the brain and the white matter. So of course here, there is no notion. I mean, the space here, X is just an index rather than physical space. I mean, there is no order. You have to choose an ordering of the neurons, of the locations. And this is why the ordering is no longer like in a one-dimensional cortex. You can certainly spot that there is a left and a right hemisphere. I think this is quite visible because this matrix, it still looks like in blocks. So it corresponds to right hemispheres and left hemispheres of the brain. You immediately see that this W is highly heterogeneous. So when you're looking at things at that scale, there is no longer this nice translation invariance that we discussed, and that is valid for small cortices. And very importantly, what you're seeing here in color is not a number, but it's an expectation of a number. So what we are seeing here is not just what happens to a single individual, but these are sort of averaged quantities across individuals, across measurements perhaps of the same individual. So what I'm trying to instill in you is the idea that, well, if we want to start working at these scales, we'd better have methods for which W is effectively readable rather than, it can be imported from data and it can potentially be random. It's very hard for me from here to detect how are you, reacting to these slides. So I would just pause for a second and ask if you have questions or comments at this stage. Just speak up.
I have a question, if I may.
Yeah, of course.
So this W are expected values, right?
Uh-huh.
What's like typically the order of magnitude of the number of measurements?
These are normalized, so these are numbers that can easily run between 0 and 1. So I don't know actually the number of connections, if this is your question, that there is.
Well, so my question will be, if these are real life measurements, then Like how many people are typically measured and
Oh, that depends on the data sets that you get. So there can be data sets with as little as 10 patients and as large as 100 patients. So that really depends. Or I say patients, but I should say humans. And then it also depends. Now this is an example that really comes from the human brain. Yeah, so I lifted it from a paper on the human brain by Rosen and Halgren that I can give you references for. That I think that was about of the order of I think it was of the order of dozens or tens of individuals, not hundreds. But also you can have other type of data set that come from mice, for instance, or other animals. So it really varies enormously. There is not like a canonical number, and in fact, I'm not very familiar with it. But since, I mean, I don't know if, I mean, in fact, it was probably with you, right? We saw that the tiniest change in the matrix that you get in the W matrix that you get can induce very different patterns. What I want to point out here is that it makes sense to not take W as being a real valued function, but rather a real valued random field. And that's what we have to study a little bit today. Any more questions? I'm really having shivers, you know, just going back to when we were teaching on Zoom. I don't know. It feels a little bit like that. Can I go forward? Okay. So here I want to just gently tell you how a typical uncertainty quantification problem happens. So uncertainty quantification is a word that has an enormous amount, an enormous connotation. It means many different things to many different people. And so I'm trying to do my best here to really specialize it to what I need for this talk. The concept being, if you internalize the mantra, left is input, right is output, is I want to exactly explain what happens in a sort of random simulation of a neural field. And I'll do that as an illustration on a very simple kernel. So a kernel that I go back to a kernel that is a function kernel, not a red kernel. And instead of showing you the, so to speak, the activity or the voltage everywhere, I'm showing you the voltage at a particular position x star in the cortex as time progresses. How can I envisage having a random kernel? Well, the way I can now picture a random kernel is that I don't have one kernel, I have a set of realizations from this kernel. And these realizations are real. So what you're seeing on the left is really the outcome of simulations in which the kernel has been perturbed. And perhaps there is the take-home message of these slides here is that I'm not restricting myself to small random perturbations. So what you see, the column maps that you see are on scale with the previous column map. So you see there is still some form of diagonal trace, but there are huge perturbations that go on off the diagonal. Of course, the perturbations that I picked here are still structured in space with some characteristic wavelength, but that is really only an artifact. And then if you toss a coin and now select one of these kernels, you find a corresponding realization of the simulation on the right. And a typical forward uncertainty quantification task is to estimate the expectation and the variance of this problem. So this is one of the many tasks that one could have in uncertainty quantification. A very often studied task is what is called the backward or the inverse problem. That is, estimate the kernels given the data set that I read. So we're now perturbing the inputs and estimating the expectations of the outputs. But often uncertainty quantifications, and this is a very exciting field that I will tell you later about perhaps, goes in the opposite direction. It goes that I don't know the kernel, I have randomness on the kernel, but I don't have, I know it's random, but I don't have it. And I now have readings of the realizations, and I have to estimate the expectation, let's say, of the kernel. And that's a backward example. And the reason why I'm not yet talking about backward is because that is a bit more technical, and also because as a building block, the forward problem is also important for the backward problem. So I just want to keep it to the forward for today. And perhaps in the next few months, you'll read about backward too. Now, what I would like to do is to do that in a situation where I have to discretize space. So there is some form of error that comes out of that, just because I'm discretizing each realization. Oh, sorry. There's something super important that I want to say. One way in which, this is a very particular way in which randomness is considered in the dynamical system. An often used form of noise is by literally adding a noisy forcing in the model. So what I'm trying to state here is that we are not, what we are not doing here is that we are not injecting a stochastic forcing at every time step. Okay, so this is something we'll do in the last 2 slides of my talk today. We're not doing that. We are literally tossing a coin at the beginning of the simulation. The coin toss gives us a kernel or another parameter. And from that moment onward, the evolution is deterministic. So there is randomness because there is randomness in the input, but the system, the evolution equation per se is deterministic. We will do later something about stochastic stuff. And again, this really requires a specialized treatment that is not, it's really non-typical, it's not the usual one, but it's necessary if one wants to do backward uncertainty quantification. And so we want to do that. We want to, we're going to have spatial errors along the lines of what we studied last time. We want stuff to be scalable. And also what we want is that in addition to the kernel, I want noise or randomness to be injected in the firing rate, in the external input, in the initial state, in every parameter that I have. And I want it to be obviously provably accurate in the sense that I want to be able to control how to do that. So what's a tentative strategy in which this could be achieved? Well, we can discretize the integral lightheartedly, or perhaps we could use one of the schemes that you've seen last time. And then we could try to perform a Monte Carlo simulation. By Monte Carlo, I really mean what I told you earlier on. So a Monte Carlo simulation is the one that you're seeing here. I extract a set of coin tosses. I evolve the system and many times, and then I take statistics at the end. Can I just cross-check that the word Monte Carlo simulation perhaps it's not new to you? Or is it, can you put your hands up if Monte Carlo simulation is something new to you? You've all seen it. 1, okay. So what I think I'll do now, okay, and it turns out that these 2 steps, namely discretizing integrals and perform a Monte Carlo simulation, it's a strategy, is a recipe, but it turns out it's almost a recipe of how not be able to achieve that. Because if one naively does both steps, very quickly ends up in an unmanageable problem. So it turns out that we need to do something, I wouldn't say clever, but well thought, if we want to move forward in this case. So at this point, I have to tell you a bit more about the projection scheme that you've studied last time, but I do not want to spend much time on that. And I would want to dedicate a little bit more time in the kind of what do we do instead of a stochastic, instead of Monte Carlo? What can we do instead? And I want to give you this flavor, not on the neural field, but on the simplest ODE that I can think of. So what I'll do now is I'll switch to my iPad and show you what it means to do a random dynamical system problem on a simple linear ODE that is interesting enough that we can study the scheme that we do. So let me just try to change my sharing now. Okay, so let's see if this works. You should now be able to see my my iPad. Okay. So what's the simplest problem one can think of is a linear ODE that we are all familiar with. So let's start with that. Let's study this problem. U prime of t equals lambda u of t for t in an interval 0 capital T. Sometimes I will call this interval J. And let's choose a simple initial condition to this problem, u naught equals 1. So I want to just assess what is the standard Cauchy problem that one looks at. I mean, I know we'll solve that problem in a second, and we know the solution to that. But what would this Cauchy problem looks like? It would say fix lambda in the reals and find a function u. This function u is typically a function of time. It has to be differentiable in time. So one typically takes in ODEs a function of, that is C1, it's defined on J, 0t, and it returns a real value. And you want to get that function such that the problem star holds. And I think the solution to this problem should be familiar. I hope you agree with me that the solution to that problem is e to the lambda t. So I selected really the simplest linear problem I could think of. Now, one thing that I wanted to keep in mind is that in this reasoning, because the Cauchy problem told us that lambda was fixed, and so often the dependence on the solution of lambda is not really discussed, right? So I think that in numerical, well, not in numerical, linear analysis courses, one never highlights the dependence on lambda. Lambda is fixed, is given a number. But we're getting ready to make that parameter be random. And so it is super useful if we introduce something that seems very complicated, a new function, u tilde, that depends on t and on lambda. So I'm using the tilde for this just to distinguish it from u of t, of course. But in here, I have the option of really just thinking that this is a function of lambda as well. So now let me try to state in what spirit do we perturb the problem randomly. Now, what's going to be the forward UQ problem here? I'll first write it informally in words. Is now I have to assume that lambda is a random variable. So assume that lambda is a random variable, let's say. And then the idea would be to estimate Don't write this because in a moment I'm going to change it. This is too vague to be useful, this definition. Estimate the expectation, for instance, of u of t. So in a moment we're gonna have to change this. Why is and in such that, well, of course, such that the problem star holds. So this now is a bit more tricky because we're gonna have to introduce the fact that lambda is a random variable. It is at that point really not clear what we mean by the fact that u is a random variable that has an expectation and that it solves this problem. So what is it meant for that? Let me try to make some progress on this. So the starting point here is just to say that the assumption that we're going to have to replace with is to say that lambda is a random variable. So it will map from a space of events to the reals. Sometimes we're going to denote this by saying that lambda of omega is a realization. Now, really, depending on, I don't want to insist on technicalities, but depending on how, on your background, you can jump straight into consideration about measurability of this function and then try to view in which function space lambda lives. If you want to have an easy and-on approach for this talk, really thinking that whenever you toss a coin, you are changing the value of a variable omega and a different lambda gets returned. So my tossing a coin or doing a realization means choosing omega randomly. Another assumption that we're also going to make is that lambda has a distribution. This is not necessarily the case. It doesn't have to be so, but we're going to say that. So that the distribution rho lambda is distributed in this way. Is as density. That's what I meant. Not like that, because that one is really not correct, I think. So let's make an example. For instance, you would say lambda is uniformly distributed between -1 and 1. And that means that rho lambda as a function of y, let's call it y now, is a half, well, it's a half for y in -1, 1. And it's 0 otherwise. I'm trying to use as little background as possible in probability theory, but I think everyone, oh, what's that? I think everyone will have seen probably this at some point in their life, that now you have a random variable you have a certain density between -1 and 1, and this has to be at 1/2, so that the integral between -1 and 1 is obviously 1. So this example is so simple that without thinking too much, we know immediately what the solution should be, well, of what the solution to these problems should be. The first thing one could do is to say, well, now my lambda, I could look at here and say, oh, my lambda, I think you should probably see the iPad now. You would say lambda depends on omega, and therefore I have to make premises for u to depend on omega as well, because I'm now modeling the fact that at every coin toss, I have a different realization. So what would I do? I would say, first I write down the problem in this form. In this case, t is still in the interval j, and now omega is an element of your event space. And you then have 1, I think, as initial condition. And this problem, I choose is so simple that we can really solve it, right? It feels like ut omega has to be e to the lambda omega times t. So how do you interpret this? Well, you interpreted that precisely how we studied for the kernel a moment ago. If you toss a coin, you fix lambda. That's the coin cost that I was mentioning to you about. And then from that moment onward, the evolution is deterministic. So you have committed to one particular value of lambda, and then you just use the function that you have to solve this problem. And one thing that I want to stress that is going to be very important in the remainder of the talk is that what is happening under the hood is really that, well, this is not a definition, but rather an equality. We are really using the function u tilde there, and we are we're plugging in the value of the parameters that we pick. So what I'm trying to state is that in this form of randomness, and this is something deep that it's true also for the neural fields results that you will see in a second, later on, all you have to do in these type of problems, that's, well, not all, but it's, I mean, the general philosophy of it is that now you describe your solution in terms of the parameters that you want them to be inputs, and then you evaluate the parameter at a realization to get the solution there. I'll give you a few more elements of how to interpret this in a moment, and then I'll just open the floor to questions. So what can happen now to these problems? Well, of course, all these solutions starts at 1, but you can get some realizations for which lambda is negative, and some realization for which lambda is positive. So this would be u at t omega 1. This could be u at t omega 4. I'm just stating, depending on how you extract lambdas, you're going to have ups and downs. Can I ask you to put forward any questions or comments that you have at this stage? Because I think this, even if you've seen a stochastic differential equation, which is a much harder version of that, this might be new and kind of twisted in a way if you've not seen it before. I've chosen a simple example, but I need to check something about the general principles behind it. Go ahead, ask questions if you have. Go.
Maybe a bit silly, but in this specific example, it looks like the moment generated function, no?
Yeah, in this case, yes, it ends up being a moment generating function because of how I picked up. Yeah, in this general case, but imagine that imagine that this could be now casted in general forms, and we will do that perhaps later, or perhaps not. You know, we do that in a situation where you have a generic nonlinear problem that may depend on time. It will depend on you, and it will depend on many parameters. Ym. So in those cases, I mean, this one looks like a moment generating function because the special solution that this problem has is an exponential of that type, but yes, in general, it won't. Any more comments or questions? Because if not, I have one for you. Okay, so I told you that at this stage, the task, so this is not yet uncertainty quantification. I'm just describing to you what is the system that we're now studying. An uncertainty quantification in this case would be to estimate the expectation of u of t. I put now a dot here just to indicate that I'm considering now the random version of u. And I want to, this is not a trick question. I want to ask if you have an intuition for what's going to happen as t goes to infinity on average. Go ahead.
It's going to be infinite, because half of the solution is going to be 0 and half of them going to be infinite. And if I try to average infinity with 0, I would expect to get infinity.
Okay. I like this answer. Any other comments? Has anyone, so I was not as sharp as Nico when I said this problem. And to me, I thought, okay, they'll even out. I'm gonna have some solutions go to 0, some not go to 0. I would think that perhaps they would even out. And what I was asking myself, I think, is a different question, which is, what's the probability of this being 0, which is a probability a half, right? I hope you agree with me. Which is the same as the probability that that thing will blow up, let's say. So in here, basically, I was trying to say, well, if I ask the questions, should I expect that my solution blows? What's the probability that my solution blows up? It's 50%, because I've chosen the lambdas to be evenly distributed. And so 50% of the time, I'm going to get a blowing up solution, 50% not. But the task that we're looking at here is different. The task is now to estimate the expectation. And that is a subtle thing. So the intuition that Nico has is correct, but we can also now just try to compute it. And this will be very, very helpful. The uncertainty quantification now is to estimate the expectation, not to ask its limit, but we get the limit for free. So let's try to do that. That's something that we can work out together. It's actually relatively doable. So if I want to have the expectation of ut, I should integrate over all possible events the thing that I want, so ut omega times the measure, well, integrated over the measure that you have. Now, I'm writing this down, and if you've never done a probability, measure theory and probability, probability theory through measure theory, this may look a little bit unsettling, or perhaps you don't know what this symbol means. But the fact that I picked lambda to have a density, it means that the expectation can also be written like that. U T y, U tilde, in fact, T y times rho lambda y in dy. So in here, I could have written lambda inside here, and then taken times the density of it, but I've chosen a dummy variable y for lambda. Is this? I mean, I think so what I'm now highlighting with the dp omega, you don't need to know, and you don't need to understand, but it's crucial that you understand what this is instead. So if I were to say, what's the expectation? Well, the expectation is that I would expect that you are on board with this. Can I cross-check that you are all on board with this? So if I have the expectation, well, take your parameter y, multiple, that's the random variable that you have now, integrated against the density that you have between -1 and 1, because we have a uniform density. Well, the density is defined on -1, 1. And so that now gives us a half integral between -1 and 1 of e to the yt. So you see, I could have written lambda there, but I'm committing to have these dummy variables. So the variable, the density is 1/2, which I already wrote in dy. And if you carry out that integral, that turns out to be the hyperbolic sine of t over t. Now you can plot this function. And in fact, if you plot this function, you can write it here. You find out that this function blows up. So this is the intuition that I didn't have, but some of you had perhaps. That on expectation, this thing blows. So that's the E of ut. Now, in this case, and you could also pick up variances here too. And then the idea is that if you try to pick up the variances, then you would be able to put some form of confidence intervals, let's say, around the expectation. So one thing that you may try to do, but I will not do that. I think this is fun if you want to have an exercise to do in a rainy day. You could just try to set up lambda to be uniformly distributed between 0 and 1. No, pardon, between -1 and 0. And in that case, what I found, which I think it's correct, but mostly because Wolfram Alpha made integrals for me, is that in that case, I could estimate the expectation to be decaying this time. But something interesting happened to the variance for me. So this would now be the expectation. But something interesting happened to the variance in that case, in the sense that the variance was increasing and then decreasing. Yeah? So if I now have to think of a confidence interval for this problem, where this could be like plus and minus variance or plus and minus 2 variances, it would not be monotonic. It would just have a fat region, a large region somewhere in, and then a thinner region out there. But can I ask you to take this with a pinch of salt? Literally, this was done yesterday evening while I was realizing I wouldn't be able to come there. So I tried it on the back of an envelope. This is what came out. Just try it yourself if you fancy. Now, is this clear? I mean, this is a minimal example, but I want to make sure that we are on board, because now I still haven't told you anything about the numerics, and now I'm going to tell you the numerics of it. So in this case, we could compute the expectation. But in the neural field case, or as well as in any kind of set of complicated nonlinear ODE case, we wouldn't have a formula, because we wouldn't have E of yt. So what we would have to do is rely on simulations for doing these integrals. And so the idea now is I want to give you the Monte Carlo version of doing Monte Carlo approximation. How would the Monte Carlo approximation look like? It would just say, take independent realizations of lambda. So let's say it was between -1 and 1. You now have these LK samples. Then you would simulate up to time, let's say t, whatever t is, and obtain u tilde t for lambda k. This, of course, comes in now a set. Yeah, you would just do, let's say that you would have k running from 1 up to m. So you now simulate forward, and then you would just produce an approximation, E. I'm going to put MC here with M samples to just signal that this is an approximation to the true value. And that one would be 1 upon M times J, well, K, 1 to M of U T Y U tilde T lambda K. So what's happening now is just I should, this this should be a function of omega, but I know it is a function of omega. I think the notation here is crucial. This U is a function of omega, but I know that, what is it? U, where is it? Here. UT omega is actually U tilde of lambda omega. And so I replace the UT omega by the U tilde lambda omega, and then I've got only K samples. So this is the same as having lambda. I mean, I don't know if this is transparent, but this is to say that lambda K is lambda of omega K, yeah? Now. And then we average out using Monte Carlo simulations. So the question that you would have as a numerical analyst is always the same, is to say, what's the error that you make by discretizing? And in here, discretization is this thing that we've just seen with M samples. And this is all fine and good. And I think what I've illustrated to you is the plain vanilla Monte Carlo, as one would call it. There are many variants of Monte Carlo, and what I will tell you here, it doesn't do justice to Monte Carlo, but the rule of thumb, yeah. So this is something of which what you typically expect from a Monte Carlo simulation is to get order square root n convergence. Okay, so I'm a bit shaky here because I haven't proved this for this particular case, but in Monte Carlo simulations, that's typically what you get. So you get slow convergence, but you also get a very easy implementation thing there. You just have to implement and simulate. Any questions before I move on and tell you an alternative way? So now that you saw it, perhaps I hope you, I think it is possible that perhaps if you didn't know the term Monte Carlo simulation, now that you saw it, perhaps it is a little bit more familiar to you. There exist alternative ways of doing that. And every scheme has its own merits, and I'll discuss merits and pitfalls of every scheme, of both schemes, in a second. So what an alternative to that is to use stochastic collocation. sometimes people call this polynomial chaos expansion. These two terms are a little bit like that. And what's the general idea of that? The general idea runs as follows. We've just seen, pardon. We have seen that the expectation is computed exactly by an integral. And don't we know quadrature rules between -1 and 1? Yeah, that's, in fact, in our case, this is even natural because we have done quadratures already all over the place to approximate the neural field. So one could decide to approximate this in a different way from that we have seen before. You could say, let me approximate that by where psi j and yj are quadrature nodes and quadrature weights. So this is a fundamentally different thing that says, well, first of all, I hope you realize that the expectation, so even if this is a random quantity, the expectation is a deterministic quantity. It's expressible as an integral. So I can apply standard quadrature rules for that. And now I have a different estimate for this. So I'm going to call this, I'm going to call this thing ESC for stochastic collocation with M nodes. And I'm going to now ask myself the same question. SC. So we should take a break now because to just pause for a second on this. If you for a moment think, so imagine that you're doing this on the huge neural field problem. Yeah. What is the expensive part of a Monte Carlo simulation? Well, the expensive part is to simulate up to time t. You typically flip a coin, get your lambda, and then you can also visualize sending in parallel all these seeds to neural field problem. And the long and tedious thing is to to simulate the neural field up to time t for that particular value of lambda. But in this respect, the two schemes behave in the same way. Because if I want to compute this sum, all I have to do is still to simulate the neural field for some value of lambda. That's exactly what is being said here. There is no difference between them in terms of how the schemes operate. In fact, the only real difference is that these realizations are all scaled by a weight 1 upon m that is identical for all k realizations. And in here, we just have different weights, right? The weights is psi j, rho, lambda j, but this is just nothing different. Just reweighing simulations. So this makes them very appealing, so to speak, schemes. And now the question is, what is their convergence rate? And it turns out that this is a massive question that it really depends. So what you can show is that if you are in a situation when you have when your function is regular in the parameter y, so if I were to tell you how is this u tilde, is it a smooth function of the parameter? In this case, yes, I took it as the exponential. Pardon. So I took it as smooth as I can possibly think. Yeah, it's a very smooth function. If your function is of class CK, yeah, CL, then in here, you have an order of m to the L. So the more regular your function is, the faster your conversion goes as m goes to infinity. So this is, I should have stated, sorry, I think I've made a mistake here. Sorry, let me correct this. Pardon. So this cannot be square root m. This should be m to the minus a half, because these are all trends as m tends to infinity. So you would like that thing to go to 0. No, square root m was blowing up. And similarly here, you're gonna get m to the power minus L, where L is the regularity parameter of u. And then you can get a feature that is called superconvergence, or actually spectral convergence, pardon. That is, if you prove that the function in y is analytic, so analytic means more than smooth. It means that you take infinitely many, it has infinitely many derivatives, and also you have that power series converge for every point in their domain. Then you converge faster than any power of any polynomial powers of L. So this is really a striking result. It says, if I know for a fact that my function is smooth, like the one I picked here, then my method of choice should be the stochastic collocation. Because with very few realizations, with very few m, I just go down to machine accuracy, basically. Now, this my presentation, yes.
How does
Go
this
ahead.
for infinitely differentiable functions? Because then we would have m to the minus infinity, which...
So the way you phrase it is that if you have a function that is differentiable, and for this statement, you don't need, you need more than infinitely differentiable. Huh? You need more than C infinity. You need infinitely differentiable and you need convergence of series, basically. So this is it's called analyticity, this property, which is more than differentiability. But the way you phrase it is that you go faster than this for any L, however large. Do you see what I mean? So one way to say it is to say, well, in fact, you will see an example that there's going to be an exponential to the power m minus m there. So you get really an exponential convergence with the e. You see what I mean? The
Yeah.
like. Yeah. So that is faster than any power of L. Mm-hmm. Any power of m to the whatever power, you get a faster one. So that's called exponential convergence or spectral convergence. Now, what I was saying is that this presentation perhaps leads you to think that stochastic collocation is a fantastic method and Monte Carlo simulation is a bad method. And no, there is like problems as well that crop up that I haven't talked about. And you will see these at the end of the slides today. For instance, one problem is that typically whether your u is lambda or not, so how large is L, how large is your differentiability class, depends on the problem at hand, and it depends on assumptions that you make on the noise. So it is not always the case that you can have the smoothness. Sometimes you have rough noise, you don't have smooth noise, and if there's smooth data in Y. And if you have non-smooth data in Y, then sometimes you cannot do much. This problem, this scheme is unaffected by that. In some sense, it's not feeling this, but your L can be very, very small. There is another, and I think much more limiting problem from stochastic collocation. In this case, I've made the example of just one parameter. But in a real-world scenario, you will want to have many parameters, perhaps infinitely many of them, if you're looking at a function. When you have, imagine that what you want to do is you want to take a random parameter for every entry in the matrix that we have extracted the other day. You could decide that your W kernel matrix is random. And this means you have a lot of random parameters. In that setup, stochastic collocation becomes hugely expensive because you now have to take an integral over, this becomes an integral over Rm, like a very large parameter space. And carry out this becomes very inefficient because this thing works with tensor product. So first off, you have a combinatorial explosion of the number of grid points that you have to explore with quadrature. So that's one pitfall. Another pitfall is that the beautiful convergence rates that you get degrade with the dimension of your problem. So this idea that you're going to get faster convergence becomes less and less so if the dimension of Y is large. And so this typically means that you do stochastic collocation if you have few parameters and your noise is smooth. And otherwise you do sophisticated Monte Carlo, so much more sophisticated than the one I explained here, Monte Carlo simulations, when you are not in this condition. And I think in this way, I've given you more or less a view of, I think, to view the rest of the talk. So what Francesca is working on, and that's what I would like to talk to you for the next 15 or 20 minutes, perhaps, is she is working out how to do stochastic collocation for neural field problem. But there is a big important stumbling block that she also has to solve, that it is not at all clear for a neural field problem what it means to be a solution, really. So in here, I picked up an example that is trivial enough for which the solution can literally be guessed. But for the problem that Francesca is studying, namely the one in which you have a neural field, so your solution lives in a Banach space, you really have to get into the nitty-gritty details of what it means for a solution to be measurable and in what sense, and what is the ODE that satisfies. For instance, I've swiped under the carpet for you the fact that this is meant to be a solution for almost all omegas, not for all omegas. So you want a solution that satisfies this problem up to sets of measure 0 in the probability P that you're considering. So this type of technicalities that you really need as a building block for whatever method you want to use is part 1 of Francesca's work. And part 2 of Francesca's work was to look at it using stochastic collocation. So after she has developed this sort of basic fundamental knowledge about neural fields, she has worked a little bit on the stochastic collocation method. So in the next 25 minutes, I mean, the way the lecture is going, I want to give you a hint of that very quickly. Do you have questions and do you want to break? You cannot not say anything to my last statement. Huh? You're only the 5 of you. Can you decide amongst yourself if you want a 10 minutes break or not?
5 minutes.
5 minutes break. Let's reconvene at 11:16 then.
Oh, I see, that's the business. Okay, so that's all fine.
Yeah.
Oh, then that's the, okay. Now
Yes.
Yeah.
Yeah.
Yeah, so. Dat jij ook non-profit researcher dan Daria aan het bericht gestuurd?
Voor de 19e.
Ja, ik zei voor de 21ste, maar maandag is natuurlijk Pinkster, maar eigenlijk wel steeds tot
Oh,
Pinkster.
zo.
Dus dan heb ik geen tegen.
Ik zal het nu even dat
Ja, dus als je. Oh, je hebt het al. Oh.
Ja, nee, maar ik zal het nu gelijk maken.
Ja, maar als je dus dan tegen haar kan zeggen voor zondag, dus voor deze zondag, dan is het oké. Dan kan ik het zondag erop zetten.
Ja, daarvoor zaterdag.
Wij dan kan ze iets eerder, dan kan zij het ook gelijk.
Okay. No, not everyone is in the room. I see. Okay, so let's switch back to presentation. Okay, so remember, I'm not gonna go through every slide here because this is basically a recap of part of what we discussed last time. So what I'm gonna lead you towards the stochastic version of this stuff. But remember that last time we found two possible ways to do the schemes. One of them was called collocation, in which we were trying to to collocate the equation at nodes on the cortex. That's the one you've implemented. And then there is the Galerkin scheme, and I am aware I have dodged the question as to what are the benefits of both. That was not very, I didn't address it properly. I thought I would address it eventually. I have no time to address it properly, so I will leave this with like a bit of mystery, but the bottom line is normally when you're looking at interesting geometries in PDEs, Galerkin is the way forward. We have also seen that these two schemes, the Galerkin and the collocation, they turn out to have a similar flavor once you look at the right projector scheme. And I'm gonna basically skip on these things because, yeah, otherwise this is gonna get really too much. Perhaps for the people that care about this is not really strictly essential to follow the rest, but I think it may be a nice touch. The way to just carry out this analysis and much of PDE analysis is to abandon the notion of an equation on Rn like we're used to do in standard ordinary differential equations. So if you look at the sketch on the right-hand side and think that x was a point in Rn at every time t, when t moves along an orbit, what you're going to get returned by u is a vector in Rn, a set of n coordinates, morally speaking. The way to make progress in PDEs is to think that at every time t, you're going to get a function of space out. So this is what takes you to speak about Banach space valued ODEs. And when one tries to address PDEs rigorously, this is basically the only way to make sense of them. That's very natural with respect to them. It turns out that neural fields are very forgiving with respect to PDEs. So the classical setup is you take for the ambient space, the Banach space, either continuous functions on D, CD means continuous functions on the cortex, or L2 functions on the cortex. You can take other type of functions on the cortex. But the important thing that people have worked out in the early 2000s is that neural fields emit classical solutions. So so normally, to make sense of solutions of PDEs, you have to work with notions of solutions that are weaker than, so in which your solution is not differentiable everywhere, for instance, in time, yeah? And for neural fields, this doesn't happen. And I have prepared these slides. They are just a complement to the stuff that I wrote on the board, but let's just move on. Okay. So perhaps this is the important bit that I want to mention, and let's stop here. So remember last time I spoke to you about two possible ways to discuss a scheme, and I didn't present this proof of convergence. But here is a very important take-home message that I want you to get, and it's really new stuff, as in it came out last year. So this is when I worked out on this stuff. The quantity of interest, when you want to look at what is the error that you make with a deterministic problem, is the stuff that is in the middle. So you see there is an inequality here, and the inequality is u minus un cjx. So over there, I'm taking a norm, the norm of the solution. U is the true solution. U sub n is the discrete in space solution. And CJX is just a complicated and compact way to say that I'm taking the worst case across all times of my solution. So if in black, I depict a standard solution, and in red, I picked the solution of the approximate problem, I could decide to measure the distance at time t according to the norm of the space where I live, and that is at time t, or I could decide to take the worst case across all possible time, the maximum of the distance, to be my measure for the error. And this is a strong way of measuring errors. So what these results states is that you're interested in that error, but actually all you have to do to determine the convergence rate is to look at how the solution behaves according to the projector that you have. So I don't know if this is really interesting or intelligible from your side, but I want you to concentrate on the bound on the right-hand side, the one that says m times u minus p and u. P and u is different from un. Un is the approximate solution. P and u is what the projector does to the true solution. So remember, we had two projectors. One projector was associated with the collocation scheme. Another projector was associated with the Galerkin scheme, but they were all represented formally by Pn. And so what this theorem states, as you see, u minus p and u appear both on the right and on the left as schemes. Yeah. So this is, I would say, a very interesting result that states, if you're interested in convergence and convergence rates of this problem, you have a sandwiching estimate that says the convergence of u minus un, so how fast that thing gets to zero as n goes to infinity, the thing in the middle, is exactly the same rate at which the projector approximates the true solution. Because you have from both sides u minus p and u. And this is very powerful because typically you know a priori how your projector behaves. So if I now want to study if a neural scheme converges, all I have to do is just lift a finite element book. They will tell me for this particular cortex, if you use these elements and this particular projector expects this convergence rate on functions, I just read the convergence rate, and that is the convergence rate of my neural field over all time. So it's a rather strong result. I don't know if you care about what I stated. Yes. Yeah, is there a question? I don't see you very well.
Is smaller than 1?
Sorry?
Can m be smaller than 1 in the interval between 0 and 1? Because I think then the inequalities don't hold anymore, right?
I think in this case, yeah, you are right. So what is the constant m? So it's very unlikely that this is, so for time intervals that are, so that constant has an exponential to the power constant times t.
Yeah.
T being the time horizon. It's exponential positive, so it's very quickly going above 1.
Yeah.
In that case, I would have to flip. I would have to reassign the change of m. Let's say so, depending on the time, depending on j. So the correct way to say is that this is m sub j, and then depending on the value of j, I would have to just flip them.
Yeah.
Thanks for pointing these out. I think you might have spotted now an errata in my published paper, but I don't know if I wrote it like that. I'll have to cross-check. And this is done under the assumption that your projector is well behaved, namely that you see the assumption there is that P and V goes to V it converges for any point in your ambient space, which is true for many cases, but not for all cases. In fact, it turns out that the most interesting schemes don't satisfy that property. And in that case, I have other results that are only one-sided, so to speak. But the moral is the same. Let's just not get ahead of ourselves. Let's just not get into it. Sorry, that's what I meant. So effectively, the take-home message is that as of 2023, we can now really build a full map of schemes. We have the collocation family of schemes. We have the Galerkin family of schemes. They both dependent on phi. Remember, those we're seeing interpolating functions or Galerkin functions. And now you also have a choice, this is typical in numerical analysis, of what basis do you get? Do you want a localized basis, by which I mean a basis with local support, like the 10th functions that you're seeing? Then you're looking at a finite element. And so you have collocation finite element and Galerkin finite element. Do you prefer instead having bases that are global? They typically means you converge faster on regular data at the expense of doing more work, but you have typically fewer blocks, fewer numbers. Then you have a spectral method, spectral collocation and spectral Galerkin. And what we have implemented, what you have run in tutorial 2, is a finite element collocation scheme. So it's on the top quadrant up there. But in the projection paper that I linked, I went through 4 examples, all of which are coded. So you can also have a look at that. And I promise I will not bore you with this, because I think, why would I do that? Anyway, the upshot is that all schemes behave as expected, and I bumped into new schemes that I didn't know they existed in this way. So, for instance, I now know that if I have a problem in which I have a simple cortex between -1 and 1, but no periodic boundary conditions, I can still use FFTs. That's the top right quadrant, to run schemes with exponential accuracy in space. That's the top right quadrant with Clenshaw-Curtis quadrature, but let's just not get ahead of ourselves. Let's not just get into it. Sorry, also, I think my concentration is degrading now. I feel worse. So I'll try to close it soon. I told you that I would have to talk about stochastic problems, and so far I've just made the prelude in which I was still talking about numerical schemes. So let's now get to the stochastic problem themselves. This is what Francesca has worked on. To fix the idea, I mean, remember now we have, in my previous slide, we have parameter lambda that was random. Now here I have a neural field. Remember, remember a neural field like that. It has initial state V, external input G, synaptic kernel, and rate functions, and out comes the voltage. So now so V here is an initial condition that you can take to be deterministic, like the cosh function that you take. Francesca studies the situation in which this initial condition is now a random field. So now whenever you toss a coin, when you evaluate omega, out comes a function of space. So here on the right-hand side, you're seeing what happens in a particular situation where we pick functions of space, a random field. I think these are 100 realizations in a given function space, whose average is what is on the top. So I take the top function as being the average out of the realization. So what I'm trying to impart here as a concept, there is no need for you to process all the function spaces in this talk if you don't care about them. The idea is that now I toss a coin, and instead of extracting a parameter, I extract a function of space that is continuous. So that's what it's meant. And what Francesca proves is that if the randomness comes only from the initial state, then there is a well-posedness of the problem in the voltage. So the basic result that you have to show is to say, in what sense does a random initial state lead to a random solution? And this is what she does, interpreting this problem rigorously on the appropriate function space. And then you can mix and match. If you have multiple sources of randomness, so in here I'm making an example in which you have an initial state as well as an external input. The function g is an external magnetic input and a current input, for instance. There is no restriction. You just have to be more careful about how you define the solution, but you can still do that. And the regularity of the noise determines the regularity of the solution. Okay. So now we have to somehow discretize the problem. So where are we with respect to the simple exercise we made before? In the exercise we made before on pen and paper, we had a single parameter lambda as the outcome of a coin toss. Now we had an infinite dimensional object that came out of tossing a coin. So now what Francesca looks at is a situation that is intermediate, in which you have countably many, but finite, sorry, in which you can express those functions like as with countably many modes, so to speak. And once you truncate this, you only have finitely many of them. So this is a bit technical, but is to say, the idea is that the function v omega, you can look at the blue box where it says example truncated KL expansion. You can see Vx omega can be expressed rigorously by its expectation plus a superposition of modes. That is a tricky writing, but the important thing is really the y sub j. Y sub j are now infinitely many parameters. So they are all numbers between -1 and 1 that are random and identically distributed. Before we had just a single scalar, and now we have m scalars, y1 through to ym, that give us a random field. And this is a fundamental assumption to discretize randomness. I mean, it would be spectacular that you didn't have questions on this. So if you've never seen this thing before, I'm throwing at you literally research material that I would normally give in seminars. So is this being passed or not? I don't want to speak on my own for the next 5 minutes. Do you understand what I just stated about V? I don't see any reaction at all. Do I have to go through it or shall I move on? Can you even hear me?
Yeah. Yeah, I think I could roughly follow what you were talking about.
Should I move on or should I just go back and explain this slide again?
For me, you can go on, but no idea.
How about the others?
For me, you can go on. Yes.
Okay, so now let me cut a long story short. What we now do is the following thing. We have a function u in which we discretize space first. So from u, you go to un. And now your parameter is also, your problem is also depending on all these parameters y. And on each of these parameters y, we do stochastic collocation. Francesca does stochastic collocation. So she doesn't try to do Monte Carlo, she tries to do this arrangement there. And the idea is that this thing works like a Monte Carlo scheme, except the parameters are given to you by quadrature rules. And what she shows is that the cumulative error splits There is one error that is associated with space discretization. That's the one that we discussed in the past slide, where I showed you the norms between u minus un and the projector norms. And there is also an error associated with the stochastic collocation. And what she proves, just concentrate on the last box, is that the cumulative error in the right norm, and let's not get into the norms, is something that goes like n. So n in this case is the number of grid points that we use in the collocation. It goes like n to the minus k. So in space, you decay as fast as minus k, where k has to do with the finite element discretization that you take. So it can be 2, it can be 3. It depends on which type of elements you choose and which type of quadrature you choose. And then you see exactly what I meant earlier on when I said you're going to get exponential convergence. So in that case, you see that you're summing together e to the rj qj, and you have rates that are exponential in nature. In this case, m is the number of parameters that you have, and qj is the number of nodes that you take in the jth direction. So in other words, if your noise is smooth enough, if you have smoothness defined in the appropriate Banach space sense, you're going to get exponentially fast convergence here too, which is a spectacular result. There is a proof of how Francesca does it, but I'm not going to go through it. And this is now an example in which Francesca is showing us how this can be put into practice. So you have on the x variable, you now have a neural field with just one dimension. So you can think of it as being the ring that you simulated in the first tutorial. And G is now it's an external forcing. So on the top left, you're seeing that she picks an exponential forcing in which the forcing is made random. How so? Well, the forcing is made depend on a speed c, and the speed c depends on random parameters, y1 through to y6. And all of these parameters, you can just about see it, that is wiggly a little bit with noise. That's the expectation and the variance of u. You just have 6 parameters here. And just with 85 nodes, 85 random nodes, this is an outstandingly small number because you are trying to cover a 6-dimensional cube here of parameters. You're making integrals in a 6-dimensional cube. She manages to basically get to machine accuracy. So this is just a very economical simulation. As I said before, this only works because we are talking about 6 parameters. If there were like 60 or 80 parameters, also the convergence rates would be great. Let me not do that. Let me not do that. Okay. I just want to spend literally 5 minutes because I don't think I can cope with anything more. That states that is a little bit about what Khadija is working on. So I told you Francesca is mostly working with a situation in which the neural field is a deterministic object, is a deterministic evolution equation in which the parameter is random. And that's the basic for doing forward UQ and backward UQ. But there are, of course, other use cases, other ways to inject stochasticity in the system. And the classical way that people do in stochastic differential equation is to add noise to the forcing term. So morally, this looks like a deterministic evolution equation plus a Wiener process plus noise that changes in time. That's the classical way in which SDEs are looked at. What Khadija does is she takes that viewpoint. Then what she then says is, oh, I have a neural field. You want to put noise. I still have to do spatial discretization. And then I have to look at some form of time stepping of this stochastic process. And what she proves is that the error estimate made for the projection also carries through to the stochastic case. So this is very exciting. It just states in expectation, the error that you should consider has got also to do with the expectation of the projection error. And then based on that, so we are sure that in space, we're doing as best as we can if we select the right projector. And then she's now looking at a way to time step stochastically this process. So if you have ever time stepped a stochastic differential equation, you will have heard a scheme called Euler-Maruyama, perhaps. And what Khadija is doing, which is also very exciting, is she's looking at neural field version of Euler-Maruyama in that respect. She uses both additive and multiplicative noises, and in fact, she finds out the error convergence that we expect. So those schemes are typically converging with low order. So order delta t to a half is just a thing in Euler-Maruyama world. When the noise is additive, she finds better convergence rates. And so this is another trace that we are now taking. We are saying now that we have a theory for how these schemes develop, we start looking into noisy systems. Last thing I want to mention is that this is really only the beginning for trying to do realistic cortical simulations in the presence of data. So last week, just after I finished making these slides, Khadija showed me a fantastically exciting simulation, which I will not show you because I very much hope that she will one day intersect you and perhaps present her own. She has shown me the first data and the first situation in which we are performing a so-called data assimilation task. A data assimilation task is a task whereby you do not do a time stepping, as I'm doing here. So as Khadija is doing here, she's just assuming she's choosing K, she's choosing W, she's choosing the sigma, and she's propagating forward the solution. But very much like people do in weather forecasting these days, you can simulate a system forward subject to some readings that you have of the data set. So for instance, the way this is very rough. I'm trivializing now this, but the way you can make a weather forecasts for tomorrow is to not simulate Navier-Stokes on geophysical flows, but to simulate, to make that prediction based also or resting on also all the data sets that you have, because you have some readings of pressure, some reading of velocity fields locally. And so typically the prediction that you make is refined by the data that you read. Now what Khadija is doing that with actual data from a rat cortex. So collaborating with people in Nijmegen, she's now looking at predicting the state U of a neural field, the voltage of the state U, subject to data sets that are read in real time in the cortex. And she's really finding fantastic agreement. So it turns out that it is possible to carry out the prediction also with the data set. This is obviously very exciting, and it would basically not be possible without the theoretical developments that you have seen in this course. And I realize that this is only giving you an appetizer for what is happening, but I think it's probably a good place to stop, and I'll let Khadija and Francesca be the speaker next time you see them. Do you have questions for me before we close this meeting and the course?
I have one question. Can you hear me? Sorry.
Yeah, can you speak up a little bit, please?
Oh, okay. I'm curious about your PhD student. What she does is like use the data, the data from the experiment to adjust the model itself to adjust the parameters.
Yes, so let me just give you a flavor for that. So do you see the equation that is written on the board? Do you parse that equation? So the du equation that is written on my slides, think of them as A being -1, so that you have the standard neural field, yeah? And let's assume that now A is -1, and K is representative for the matrix W that we looked at. Now, what Khadija is working on is the following. I have a simulation up to time t. Okay, imagine that I am somewhere in time with my simulation and I've got time t. I've arrived there. Together with the simulated data, I also have readings at selected times and at selected places in the cortex. So if you now think that if you go back to tutorial number 2, we had all of these nodes in the cortex. Imagine that on selected places in the cortex, I can read calcium imaging or some other form of signals that are the reading of U. So at time t, I have both my simulations and all the readings at some points. With all of these data set, some of them are numerical coming from the model, some of them are data. I want to predict U at t plus delta t. So at the next time step. If I only have the model, I have no data. And that's what you have been doing with tutorial 2. You have been predicting using only the model. But I can also say I get my next solution so that it minimizes distance with all the data set that I've read in the past. And so you estimate U, the state. But also if you want to estimate parameters, so if your task is not to estimate the state, to estimate parameters, so for instance, what is called A in these slides, you can do that too. It turns out that is a simpler task than estimate state and parameters together. But she estimates both states and parameters, for instance, A. Have I addressed your question?
Yeah, I understand what you mean. So if it's a bit like now it's like a popular concept of a digital twin. It's a bit like that.
Sorry, I don't hear you very well.
Oh, I understand that what you mean, but it's also similar to the concept like a digital twin.
Digital twin? Oh, digital twin.
Uh,
Is this what you mean? Did you say digital twin?
Yeah.
Yeah. So so that's the spirit of it, even though I'm cautious about calling this a digital twin of any brain, mostly because I'm skeptical about I have reservations for neural fields. I think I've made it clear abundantly throughout these talks. So the data fit is beautiful, I think. But yeah, and that's obviously the direction we want to take, the one to go towards integrating data into models. I think we should do that on better models. So as soon as we finish this testing phase, we can then perhaps get to that stage with different models. But yeah, you're right. Any other questions or comments?
Yeah. Have you only looked at fixed time step methods, or have you also looked at adaptive stochastic methods?
So the adaptive in time, you mean, yeah? Is this what you mean?
Yes.
By adaptive? Yeah. So we have so far only looked at not adaptive methods. And I am very familiar with adaptive time stepper methods in deterministic problems. So in some sense, in fact, let me recast my answer. If you're referring it in the context of deterministic problems, then that's the answer is yes. We looked at that, and it makes no difference with respect to. So effectively, the indication we have there is that, and there is an example of that in my projection paper about the deterministic part I'm now saying, is that whatever rate your time stepper would have on an ODE, we can get it on the neural field. So in some sense, if you use a Runge-Kutta 4-5 or whatever time adaptive scheme on the neural field or on your ODEs, then I would get the same rates in the neural field. In the stochastic setup, which is a bit more tricky to me, I don't even know the adaptivity in stochastic time stepper. This is really, I'm talking about my ignorance about it. I'm not telling you what I know. I'm telling you that I don't know that there is such a thing. So the scheme that Khadija has used here are exponential time steppers, and she has been doing other Moulton schemes, but they're all with not adaptive time steps.
Because they exist adaptive stochastic time steppers.
That'd be great then to adapt.
In my PhD, and a buddy of mine has like adapted them from a more mathematical concept to a concept that is easier to understand for physicists. And made results with them, because then we could finally get rid of stupid Euler methods and use adaptive methods with higher convergence order.
So I would love to read about that, Nico. So if you pass me any literature, I would be very, very, very grateful. We are really, literally, we are at the beginning of this, and we are just piggybacking on what people do for ODEs for this. So any novelty from that viewpoint, from that camp, there is an opportunity to bring it here. And perhaps one thing to consider is that unlike many PDEs, these problems are less prone to give rise to instabilities. So if you come from doing Euler or forward Euler for the heat equation, you would typically have stiffness problems that have to do with the spectrum of the discretized operator. That is a diffusive operator for a heat equation. But in these cases, the operators that we discretize are actually compact. So they have eigenvalues that are typically much more well-behaved than a PDE, which really gives me hope typically to just port whatever people have done for ODEs to neural fields. Just because they don't seem to be suffering from the same pathologies that a PDE would do, let's say. They're more forgiving than that. Anything else we want to talk about? So then let me conclude by saying that it's been really, really a privilege to think along you and just to hold these lectures. Well, I wish you had half of the fun I had. And by all means, if you want to know more or want to just chat about similar topics, don't hesitate to contact me via email. It's very easy for me to arrange a trip to Utrecht and come and just have a discussion about these type of themes. And other than that, take care, enjoy lunch, and I'm sorry that I cannot be there for the afternoon as it was planned.
Maybe some applause.
Yeah.